Welcome to the crucial first step in every successful machine learning project, data preprocessing. Just as a chef meticulously prepares ingredients before cooking, data scientists must clean and organize their data before diving into model building. Today, we'll delve into the essential techniques that turn raw, unstructured data into meaningful insights for your machine learning algorithms. Let's transform messy datasets into valuable resources for predictive analytics and decision-making. Ever wonder how to handle those pesky gaps in your datasets? Today, we'll dive into missing data strategies. From understanding why data goes missing to mastering ways to fill those gaps, you'll emerge equipped to tackle any missing data challenge. Next, we'll tackle the task of encoding categories. Say goodbye to text labels like red, blue, and green, as we transform them into numbers that algorithms can easily process, opening up a world of possibilities for your analyses. After that, we'll ensure all your numerical features play nicely together on the same scale with feature scaling. By harmonizing your data, you'll set the stage for smoother model performance and more accurate predictions. And finally, we'll explore the art of engineering features. Learn how to craft powerful new variables from your existing data, giving your models the edge they need to shine. By the end of this journey, you'll master the art of transforming raw, messy data into clean, model-ready datasets. Get ready to unlock better predictions and deeper insights with every dataset you encounter. In the world of machine learning, data preprocessing is the unsung hero, the behind-the-scenes magician that transforms messy real-world data into a feast fit for algorithms. Picture this: you have these powerful algorithms, but they're as picky as a toddler at mealtime. They demand numbers, consistent scales, and no missing values, quite a tall order for the chaotic data we often encounter. Yet, here's the catch: data scientists devote a staggering 60 to 80% of their time to this unglamorous task. Why? Because a well-preprocessed dataset can turn a basic model into a superstar performer, while a sloppy one can bring even the most advanced algorithm to its knees. It's the foundation of the entire operation. Without it, all the fancy modeling collapses like a house of cards. So, next time you see a flawless model in action, remember, it all begins with impeccable data preprocessing. In the world of data science, one of the most pervasive challenges we face is missing data. Whether it's incomplete survey responses, sensor failures, or unfilled database entries, these gaps pose a significant hurdle in building accurate models. How we address missing data can make or break our model's performance. Make the wrong choice, and we risk introducing bias or overlooking crucial information. Today, we delve into the types of missing data and effective strategies to tackle them head-on. In the realm of missing data, we encounter three distinct categories. First, there's missing completely at random, MCAR, where the absence of data is entirely independent. Imagine a sensor sporadically failing to log temperature readings, its haphazard nature ensuring no bias creeps in. Moving along, missing at random, MAR, occurs when the missingness correlates with other observed factors but not the missing value itself. For instance, younger survey takers may be less forthcoming about income, yet the randomness within age groups keeps things balanced. Lastly, we have missing not at random, MNAR, the trickiest to navigate. Here, the missingness is tied directly to the value missing, like high earners dodging income queries. Handling MNAR requires utmost care to prevent skewing results. Each type presents its own challenges, demanding tailored approaches for accurate analysis. Remember, MCAR is a breeze, MAR needs attention to related variables, and MNAR calls for precision to avoid bias. Ever wondered how to handle missing data like a pro? In Chapter 1, we explore common strategies. First up, deletion methods. With listwise deletion, you toss out entire rows with any missing values. Pairwise deletion, on the other hand, uses all available data for each calculation. These methods work best when you have plenty of data and just a few missing values, but beware, you might lose valuable information and shrink your sample size. Moving on to simple imputation. Here, you can plug missing values with averages or modes. It's a quick fix for data that's missing completely at random, but be cautious, it can flatten variation and skew relationships. And don't forget about advanced imputation. By using predictive models or KNN imputation, you can make educated guesses to fill in the gaps. This approach shines when your data is missing at random and you need precise estimates, but be prepared for a more intricate and resource-heavy process. Remember, the key is to select the right strategy based on your data type, the extent of missing values, and the reasons behind the missing data. Choose wisely to ensure your analysis remains robust and accurate. In Chapter 1, we tackle the challenge of handling missing data in our dataset. The raw dataset is riddled with gaps, hindering model training. Through imputation, we transform it into a processed dataset with filled values, enabling model construction. Ages are replaced by the median, study hours by the mean, and grades are predicted using regression. Seamlessly transitioning from chaos to clarity, we ensure each student's information is complete and ready for analysis. Machine learning algorithms face a challenge with categorical variables, as they only understand numbers, not text labels like red or New York. To bridge this gap, we must encode these variables into numerical forms before training our models. The method of encoding greatly impacts model performance. A wrong choice could mistakenly assign mathematical relationships between categories. Let's delve into the two primary encoding techniques and when to apply each. Remember, the key to a successful model lies in how we translate these labels into meaningful numerical representations. In Chapter 2, we explore label encoding, simple numbering. This technique assigns a unique integer to each category, numbering them from 0 to n1, where n represents the total unique categories. It is ideal for ordinal variables like education level, satisfaction ratings, and shirt sizes, where a natural order exists. However, caution is advised when using label encoding for nominal variables with linear models, as it can lead to incorrect assumptions. For instance, when encoding t-shirt sizes, small is represented as 0, medium as 1, large as 2, and extra large as 3, reflecting their inherent order. Remember, choose label encoding wisely to avoid misleading your model. In Chapter 2, we dive into the power of one-hot encoding. This technique creates binary columns for each category, with ones and zeros indicating presence or absence. By doing so, we eliminate any assumed mathematical relationships between categories, making it ideal for nominal variables like colors, cities, or product types. For instance, turning majors into binary columns like major_bio, major_CS, and major_math. However, a trade-off exists: increased dimensionality. With many categories, the number of columns can quickly multiply, posing challenges. Imagine transforming 100 unique cities into 100 new columns. One-hot encoding offers clarity but demands careful consideration with larger datasets. Ever wondered whether to use label encoding or one-hot encoding? Label encoding is the way to go when your categories have a natural order, like education levels or ratings. It's ideal for tree-based models and saving memory. On the flip side, one-hot encoding shines for categories without inherent order, such as colors or cities. It's great for linear models and when model accuracy is key. Remember, with many categories, explore alternatives like target encoding to sidestep dimensionality issues. Choose wisely based on your data's characteristics and modeling goals. Ever wondered how the size of numbers can trick a model's perception in predicting house prices? Picture this: square footage ranging from 500 to 5,000 and bedrooms from 1 to 5. Without scaling, the model gets misled, deeming larger numbers as more important, not because they truly are. But why does this matter? Machine learning algorithms, such as k-nearest neighbors and neural networks, struggle when faced with vastly different feature scales. Scaling evens the field, ensuring each feature pulls its weight in the model's learning journey. Think of it as a leveling up process for fair play in predictions. Ever wondered how to bring your data into a consistent scale for analysis? In Chapter 3, we explore common scaling techniques that can enhance your models. First up, we have normalization, or min-max scaling, which transforms features to a fixed range, ideal for neural networks and image processing. Be cautious though, as outliers can heavily influence results. Next, standardization, or z-score, centers data around a mean of 0 and a standard deviation of 1. This method is great for linear models and logistic regression, offering resilience to outliers while maintaining the original data distribution. Lastly, robust scaling, utilizing the median and interquartile range, is perfect for preserving datasets with significant outliers. This technique is the most robust to extreme values, ensuring your data integrity. In summary, mastering these scaling techniques is key to unleashing the full potential of your data analysis. Ever wondered how scaling can completely transform a dataset? Take a look at this real-world example. In the original data, features like income overshadowed others, creating imbalance. But through normalization, all values are now perfectly balanced between 0 and 1. Standardization takes it a step further, centering values around 0 with a standard deviation of 1. The key takeaway? Scaling ensures that all features contribute equally to the model's performance, preserving relative relationships while leveling the playing field. Ever wondered which models truly benefit from scaling? Enter the realm of scale-sensitive models. Picture k-nearest neighbors, relying on precise distances, or support vector machines, fine-tuning based on hyperplane proximity. Neural networks crave scaled data for swift convergence, while linear and logistic regression unveil their true essence with interpretable coefficients. Principal component analysis demands equal scales for its variance dance. On the flip side, scale-insensitive models like decision trees and random forests march to their own beat, unperturbed by scaling. These models thrive on thresholds and rankings, brushing off the scale's influence. In a world of algorithms, not all models bow to the scale's command. Choose wisely, for in the realm of model scaling, not all who wander are lost. Feature engineering is the art of data science, where creativity and domain knowledge combine to craft new features from existing data. These engineered features can significantly enhance model performance, often surpassing the impact of using a more advanced algorithm. Just as in cooking, where combining basic ingredients creates a masterpiece, blending data elements like date of birth and current date to derive age equips your model with richer insights. It's about transforming raw features into a refined, more potent form, akin to turning simple ingredients into a delectable cake. Ultimately, feature engineering elevates your model's ability to uncover intricate patterns and make more accurate predictions. Dive into the world of feature engineering with Chapter 4's focus on common techniques that turbocharge predictive models. Uncover hidden insights by dissecting date, time features, teasing out day of week, month, and more. Embrace mathematical transformations to unveil underlying relationships, transforming raw data into actionable intelligence. Text features offer a treasure trove of information, from sentiment scores to word counts, empowering models to decode unstructured text with ease. And don't overlook the power of aggregation features, painting a vivid picture of user behavior and historical trends. In a data-driven world, every feature tells a story. Ever wondered how transforming simple student data can significantly enhance predictiveness? Let's delve into how feature engineering can elevate a basic dataset. Initially focusing on raw data like study hours, sleep hours, and attendance, we gradually craft more insightful features. For instance, by calculating study-sleep ratios and attendance rates, we uncover essential insights. Student A's 2.14 study-sleep ratio highlights a balance between effort and rest, while Student B's 1.60 ratio may indicate a potential burnout pattern. On the other hand, Student C's 1.50 ratio signifies healthy study habits. Beyond these, additional engineered features such as is_well_rested, engagement_score, consistency_flag, and risk_category offer deeper predictive capabilities. These derived features often outshine raw numbers, pointing to a more nuanced understanding of student performance dynamics. Ever wondered how to handle missing data like a pro? Remember, understanding why data is missing is key, whether to delete or impute. And when it comes to encoding categories, choose wisely, label for ordinal, one-hot for nominal. Scaling features? Think normalization for bounded ranges and standardization for outliers. Get creative with feature engineering, it often trumps fancy algorithms. And always remember, pre-processing is an iterative process. Refine as you learn more, but never forget to split your data before diving in. Master your data pre-processing checklist and watch your model performance soar. Let's put your data pre-processing knowledge to the test with a quick quiz. In a scenario where high-income individuals skip the income question, this is missing not at random, MNAR, leading to biased results with simple imputation. When predicting car prices based on color, opt for one-hot encoding to avoid implying incorrect relationships. Remember, random forest doesn't require scaling due to its tree-based nature. Lastly, in feature engineering, consider deriving new features like day_of_week, is_holiday_season, and days_since_last_purchase for better predictions. These concepts are crucial for successful machine learning projects. Keep practicing with real datasets to hone your skills. Remember, precision in pre-processing sets the stage for accurate machine learning outcomes.